Non-Euclidean hyperbolic geometry, axioms and parallel lines. The axioms of Euclid geometry. 1. We can draw a straight line from any point to any point. 2. We can produce a finite straight line continuously in a straight line. 3. We can describe a circle with any center and distance. 4. All right angles are equal to one another. 5. If a straight line falling on two straight lines make the interior angles on the same side less than two right angles, the two straight lines, if produced indefinitely, meet on that side on which are the angles less than the two right angles. Or, through a given point, not on a given line, one line can be drawn not intersecting the given line.
6. Pasch axiom. Let A, B, C be 3 points not lying in the same straight line. And let A be a straight line lying in the plane of ABC and not passing through any points A, B, C.
Then, if the line L passes through a point of the segment AB, it will also pass through a point of the segment BC or a point of the segment AC. Postulate number 6 is an important assumption made by Euclid, without explicit statement, and has been formulated by Pasch. Axiom of continuity, Dedekind's axiom. If all the points of a straight line are partitioned into two classes 1 and 2 such that any point of class 2 lies to the right of any point of class I, then either in class I there is a rightmost point and then in class 2 there is no leftmost point, or conversely, class 2 has a leftmost point, and then class 2 does not have a rightmost point. This axiom implies that there are no gaps or empty spots in the straight line. The parallel axiom of non-Euclid geometry, hyperbolic geometry. 5. The opposite of Euclid fifth postulate. Through a given point, not on a given line, more than one line can be drawn not intersecting the given line, whence it follows immediately that one can draw an infinity of such straight lines. A perpendicular is dropped from point P to the straight line M. The line N does not intersect line M. By means of symmetry reasoning about the perpendicular PQ, it is clear that there will be another straight line T of exactly the same kind. Further, it is clear that any of an infinitude of straight lines drawn through point P inside the angle between the straight lines N and T will not intersect the straight line M either. Hence we find, through a given point it is possible to draw an infinity of straight lines that do not meet a given straight line. Line N or T are called parallel line of line M, limiting parallel line of line M, or asymptotic parallel line of line M. The infinitude of straight lines drawn through point P inside the angle alpha between the straight lines N and T are called non-intersecting lines of line M, ultraparallel, hyperparallel, superparallel, or divergently parallel line to line M. But one can naturally also draw an infinity of straight lines which do meet the given line. They may be drawn to any point of the straight line, arbitrarily distant from the base. Let us take any point R and join it by a straight line to P. This can always be done on the basis of the first axiom. 1. We can draw a straight line from any point to any point. And so we have a straight line passing through both P and R. We call that line the intersecting lines with line M. We also have infinity of intersecting lines with line M such as PR, PS, PG, PH, PK. In the non-Euclidean hyperbolic geometry, sometimes the straight lines are represented as curved lines to make it easier to imagine the behavior of lines in hyperbolic geometry plane. That does not mean that the line are curves, they are still straight lines, but the hyperbolic plane has negative curvature, which make the straight lines behave as if they are curved. If the curvature of the hyperbolic non-Euclidean plane start to approach 0, the seemingly curved line in the non-Euclidean plane will start to behave like the Euclidean lines. The parallel lines and non-intersecting lines will converge to become the sole parallel in the Euclidean geometry, as we will see later. Consequently, the boundary straight line is the first one that does not meet the straight line M. There are naturally two such straight lines, one for each direction. Within the angle formed by these straight lines, we can draw an infinity of straight lines that do not meet line M. Lobachevsky gave the name parallel to these two extreme non-intersecting straight lines. Stretching line N a bit, we may say that line N and M are converging infinitely. Stretching line T a bit, we may say that line T and M are converging infinitely. In Lobachevsky's terms, all straight lines within the angle alpha diverge from the straight line M. To summarize, then, relative to a given straight line there are three types of straight lines that may be drawn through any point. 1. Parallel. There are two. Of each we say, parallel N is parallel to the straight line M in the direction PU. Parallel T is parallel to M in the direction PX. 2. Intersecting lines. There is an infinity of such lines. 3. Diverging straight lines. Hyperparallel. These comprise the infinitude of lines within the bundle. Why diverging parallel straight lines are called diverging? It is because two diverging straight lines always have a common perpendicular which is the shortest distance between them, and they diverges from both sides of the common perpendicular, as we will study that later. Why parallel lines are called asymptotic parallel? Because each parallels approaches line M asymptotically in one direction, and therefore they are called asymptotic parallel, as we will see later. This is the case for parallel N that is parallel to the straight line M in the direction PU. This is the case for parallel T that is parallel to the straight line M in the direction PX. Why parallel lines are called limiting parallel? Because each parallel, making specific acute angle with the perpendicular, creates upper and lower limit to the divergent parallel lines. The behavior of the two boundary straight lines in the 2D hyperbolic plane is similar to those lines shown in the 3D tractrix surface in the Euclidean geometry. The behavior of divergent parallel lines in the 2D hyperbolic plane is similar to those lines shown in the 3D hyperbolic paraboloid surface in the Euclidean geometry. The behavior of divergent parallel lines in the 2D hyperbolic plane is similar to those lines shown in the 3D surface with negative curvature in the Euclidean geometry.